Okay, we are continuing on here, chapter 15, solutions. So last time we sort of finished up talking about sort of stoichiometry involving solutions. And as we talked about, it's really the same sort of steps that you do in a normal stoichiometry problem, but really at some point, either at the beginning of the problem, even at the end of the problem, somewhere you do use sort of molarity in there. So if you kind of use it at the beginning of the problem, a lot of times you would be solving for moles. If you use it at the end of the problem, you could be solving for two things. You could be solving for molarity or sometimes volume as well. Is another very common one that you might be solving for. But the steps along the way really are the same. You want to make sure you got, again, that balanced equation. You want to make sure you convert to moles. And again, that is sort of where, this part comes into play. Using the molarity and the volume to convert to moles is a very common process. If it happens to be a limiting reagent problem, you should also at that point, figure out the limiting reagent if it is. And then obviously continue on after that with a mole to mole relationship, and then convert those moles to some other unit. And once again, here, you may use that molarity sort of equation, if you will, at the end. Like I said, either to solve for molarity or volume is another common thing that you might solve for as well. Any questions on those things we did last time? So if I'm not mistaken, I don't think we did this one, right? But I think we did the previous one. So I think this is where we left off, right? So why don't you give this one a go, see what you come up with. We're looking for the mass. So we're looking for the grams here of white solid calcium carbonate that forms when you mix 25 milliliters of 0.1 molar calcium nitrate with 20 milliliters of 0.15 molar sodium carbonate. Give you some numbers that might be helpful here. Calcium 4008, carbon 1201, oxygen, thank you, 16. All right, so take a few moments here. Again, follow those 4 steps. All right, let's take a look. So it is obviously a stoichiometry problem. We're mixing calcium nitrate with some sodium carbonate. So we do need, obviously, an equation to do that. So that's a good place to start. So we're going to do a little calcium nitrate action here, plus some sodium carbonate. And again, you should be able to recognize this as a double displacement reaction. So the calcium will go and make the calcium carbonate, which is right there. And obviously that would be a solid in this case. These guys would be aqueous. And then the sodium and the nitrate will come together. So we'll get a little NaNO3 that will happen here. Remember that you do want to make sure you get the right formulas first, and now you could go back and balance it, which looks like maybe we need a 2 there. And I think that might be it. Yeah, calcium and carbonate. All right, at this point, we are looking for basically how many grams of this guy. We are going to be putting in there 25 milliliters of this guy that is 0.1 molar. We're also going to be dumping in there 20 milliliters of this guy that is 0.15 molar. So the next thing we want to do is convert to moles, but we also want to think about, is this a limiting reagent problem? This is a limiting reagent problem. Again, we have the volume and the molarity for both of those guys, which means we could technically get the moles of both of those guys. So it actually is a limiting reagent problem. So we do need to find that at some point, but we'll first start with the moles here. So we do need to convert our volume into liters. So 0.025 liters. If we divide the 25 by 1,000, we're going to multiply it by the molarity there of our calcium nitrate. The liters there will cancel, and that would get us 0.025 times 0.1, 2.5 times 10 to the minus 3 moles of our calcium nitrate. We would do the same calculation here for our sodium carbonate. Again, dividing the 20 there by 1,000 gives us 0.02 liters. times in it by the molarity of our sodium carbonate, which is 0.15 moles per liter. A reminder that you probably want to get rid of the big M and use both of the units so you can see it. Once again, here the liters will cancel, and that will get us 0.02 times 0.15 here, something like 3 times 10 to the minus 3 moles of our sodium carbonate, or 0.003 and 0.0025. Any questions on that so far? So just like normal, we could pick one of those reactants and basically figure out how much of the other reactant that we need to use it completely up. Again, as we've talked about before, these are sort of like our starting amounts, right, of each of these guys. So I'm just going to figure out how much sodium carbonate I need to use up all of my calcium nitrate. So moles of sodium carbonate needed. And again, we would use our moles of our calcium nitrate, 2.5. Looking at the equation, it should be a 1 mole of calcium nitrate gets us 1 mole of our sodium carbonate, which means we need 2.5 times 10 to the minus 3 moles of sodium carbonate here is needed. So obviously, like before, we need, in this case, 2.5. So we have 3 times 10 to the minus 3. Do we have enough for that guy? We do have enough, right? Just barely, but we do have enough. So that means, again, that this guy would be our excess reagent. This guy here would be our limiting reagent. Any questions on that there? Now that we know that the calcium nitrates are limiting reagent, we will now use the starting moles of calcium nitrate to go from calcium nitrate to our calcium carbonate in this case. Also, it looks like it is a 1-to-1 relationship, so that makes it pretty easy. So using our limiting reagent here, which is our 2.5 times 10 to the minus 3 moles of calcium carbonate, our calcium nitrate. Doing our mole to mole relationship between the two, again from the balance equation, 1 mole of calcium nitrate gives us 1 mole of our calcium carbonate, and that gives us 2.5 times 10 to the minus 3 moles of our calcium carbonate. That obviously would be our theoretical yield here in moles, but we're looking for grams. So we do need the molar mass of calcium carbonate. So that's a 4008 plus a 1201 for the carbon, plus 3 times 16 for the oxygens. I want to say 100.1, something like that, I think. Sounds good. 100.1 grams per mole. Obviously, we will use that in our final step here to convert our moles into grams. 100.1 grams go up on top, moles go on the bottom so that they cancel, giving us looks like 0.25 grams of calcium carbonate would be produced in this case, which again would be our theoretical yield in grams. So once again, really the same steps as a normal stoichiometry problem. Again, sort of the difference using that molarity at the beginning. Also illustrates the fact that, again, you can have a limiting reagent problem, with molarity, with a combination of something molarity and grams. So again, the thing you want to think about is, do you have enough information for all the reactants to get the moles? Whatever information is given to you, whatever units, if you could get the moles, then you pretty much needed to make sure you figure out that limiting reagent. Any questions on any of those steps there? Okay, so Next thing we're going to talk about is another type of solution, stoichiometry, which is essentially what we're doing in lab, which is really titrations. And as we talked about, a lot of times acid-base titrations are acid-base neutralization reactions. And this occurs from when you take a strong acid plus a strong base. Whenever you kind of put those two guys together, you will always get two things, which is a salt plus water. And the water is basically from the H plus from the acid, and the OH minus from the base is basically how we get to water. The salt is basically the ionic compound that's left over. It is a basically acid-base neutralization is a double displacement reaction, like we talked about. And if you go through, any sort of combination of strong acid, strong base, when you put it together, really the ultimate sort of reaction that's taking place is one of those driving forces for reactions, which is basically you're making water. Is basically what is happening in that reaction. So when you take something like what we did the other day there with our, HCl and our sodium hydroxide, again, it really is a double displacement reaction, plus minus, plus minus. The H and the OH, again, is where we form our water. And our salt comes from the combination of the other two guys here, which again would be our sodium ion and our chloride ion together, making our salt. And again, if you went through and did your total ionic equation, this would be H plus Cl minus, as that is a strong electrolyte, and Na plus OH minus. Remember that we do keep water, solids, weak electrolytes together. So the water would stay together. We would get our sodium and our chloride here. The sodium and chloride on both sides, once again, are our spectator ions, which obviously we cancel out. And again, this is ultimately what is happening. Once again, that H plus from the acid, OH minus from the base, going to come together to basically make water. So that is ultimately what is happening in any sort of acid-base reaction. We do titrations, which is a common sort of process like we're doing in the lab to do these type of things. And it allows you to figure out, things like the molarity of your acid maybe, or molarity of your base, the volume needed to reach the equivalence point. So as we're doing it sort of in lab, titration, again, is that process where we typically add a known concentration solution to an unknown. So in the lab we did the other day, the acid source our unknown acid concentration, right? But we didn't know obviously the concentration of the base that we were adding. And obviously, as you did, and you will do again today, something like the sodium hydroxide up here, right? Your acid down in here. And obviously you'll be dropping your sodium hydroxide in there. We use, obviously, as we talked about, an indicator, something like phenolphthalein, that turns color near what is known as the equivalence point. And the equivalence point is essentially the part of the reaction where pretty much you have equal moles of acid and base at that point. So the moles of the acid will equal the moles of the base. And that's technically what we consider sort of the reaction being complete, because if we look at our HCl plus our sodium hydroxide, giving us our water plus our sodium chloride, you started with so many moles technically of your HCl in the titration. You had none of those guys to begin with. When you reach the equivalence point, you have basically the same number of moles on each of those guys. So at the end, you have none of these guys left when you get to the equivalence point. All that you have left really is some moles of your salt and your water. And again, that's why it's considered complete at that point when you hit the equivalence point, because basically if you used up all your reactants, basically have made all your products at that point. If you go past the equivalence point, what you're doing is making some other stuff. You will then have some of this left over if you actually go past the equivalence point, because all you're doing, if you think about it, is just dropping base into your beaker, right? So you're adding more sodium hydroxide at that point. So that's why we technically want to stop at the equivalence point in most titrations, because that again is pretty much your completed point of this reaction, where pretty much you have now made pretty much all products at that point. Again, if you go past it, you're actually adding more reactants in that particular point of the titration. Any questions on that? And again, in terms of when you do a titration like this, you know, what happens in terms of the pH is really what is changing, and you get sort of a subtle rise to a more extreme rise in the pH as you approach the equivalence point. And so we do start to see the pH rise because we are adding base in this type of titration, so the pH actually goes up. And we do typically see a pretty big jump to the equivalence point in pH. And then you kind of see a jump after the equivalence point. And as we talked about, and maybe some of you experienced it the other day, you know, if you get close to that equivalence point, you just add like one drop, it like goes like no pink to again super pink. And as we talked about, that's really because indicators work over a pH range. So adding a very small amount of volume when you get close to the equivalence point could actually change the pH a lot with just a very small amount of volume. And what that does for your indicator is it changes obviously the pH of where your indicator is a lot, even though you only added like a drop or two past the equivalence point maybe. And you'll see it go from, again, kind of like colorless to almost like a really dark pink type color. And that's because the indicator we're using, which is phenolphthalein, again, works on a pH range of 8.3 to like 10. And again, around 8.3 is colorless and obviously gets much pinker as you go that way. So as I mentioned, it doesn't really matter, you know, if you're really careful when you're doing your titrations, because if you just missed it by a drop, even though your pH is a little bit higher, the volume of where you are is pretty much the same because it's vertical as you go towards the equivalence point. Now, again, as I also mentioned, if you're not really careful as you're doing your titration, you just open that thing up and let it drain for a long time and then shut it and circle it and it gets really dark pink. You really don't know where you're at. You again could get that same dark pink way over here, which again would be very, very far away from your equivalence point volume. So that's why it says in your instructions, and most times the most important thing when you do sort of titrations is not necessarily the color if you're really careful, but as long as the volume of like sodium hydroxide you added for each titration is in the same ballpark, you know, you probably are going to be okay in terms of your calculations. And that's because in most titrations, you start with the same amount of acid, right? So the same amount of acid should technically require the same amount of base every time that you titrate it. Again, it won't be perfect because it's an experiment. Any questions on any of that? All right, so we do a lot of titration problems as well, and they're sometimes referred to as neutralization problems, and sometimes they're just mentioned like, hey, how much of this to neutralize something. That's kind of a hint. It's almost like a titration problem. So let's take a look at one here. What volume of 0.15 molar nitric acid is needed to completely neutralize 45 milliliters of 0.55 molar KOH? So why don't you give it a try here? This is, again, really a solution stoichiometry problem. So we got to start with the equation, think about what information is given to you. And in this case, we're actually looking for a volume here. Look, so once again, we're looking for the volume of our nitric acid that's needed to neutralize 45 milliliters of our KOH solution. So again, this is a stoichiometry problem. It's really kind of like a titration problem since we have a strong acid and strong base. So once again, we want to start with our equation. So that's going to be our nitric acid plus our KOH. And again, that's a strong acid, strong base. So if you're not sure, you should just write water because that is definitely one thing that should be made. Again, the water is going to come from the H from here and the OH from there. That means that our salts will come from the combination of our other two guys here. So that is K plus and NO3 minus, which gives us KNO3. Now we got the right formulas. We want to make sure everything's balanced. And in this particular case, I believe we are balanced here. So we have 4 oxygens on each side. We got 2 hydrogens and a potassium and a nitrate. So we are actually balanced. So we're looking for the volume of this guy, and we are given the molarity. We are given the volume of our KOH and the molarity of it. This is a limiting reagent problem. This is not, first off, we're looking for the one of the reactants, and second, we don't have obviously enough information here to get to moles. So it's a basic stoichiometry problem. The difference here is just going to be, we're going to use that information there to get to our moles. So that's what we would want to do first. We want to take our volume and divide it by 1,000, which will convert to 0.045 liters. We're going to times it by the molarity of our KOH. And again, the 0.55 is basically 0.55 moles per liter of KOH. Again, that is where the liters actually cancel each other out. Gets us 0.045 times 0.55. Gets us something like 0.02475 moles of KOH. Now, again, in this case, we're not interested in KOH. We're really interested in our nitric acid, and we're interested in the volume here. So we do have, obviously, the molarity given to us. We are looking for the volume. So once again, sort of the missing piece that we need to get there is the moles of the nitric acid. So obviously, that is what the stoichiometry part here is going to allow us to do. Now we can get the moles of the nitric acid by doing the mole-to-mole relationship between these two guys, which happens to be a 1-to-1. All these nice 1-to-1 relationships makes the math easy. 1 mole of nitric acid and 1 mole of our KOH. Moles of KOH will cancel, and that will get us 0.02475 moles of our nitric acid. And again, that is really the missing piece that we need there to figure out the volume using the molarity here at the end. So again, this is a little bit different than a normal stoichiometry part. At this point, we normally would use the molar mass to go to grams. But again, here, very commonly here, we're going to use the molarity and the moles actually to get to volume. And that would be liters is equal to moles divided by the molarity. So since I got the moles there, we will use the molarity of the nitric acid. And again, 0.15 moles per liter that can be used like that, or you could flip it around and kind of use it like a conversion factor where liters of the HNO3 would go up on top and our 0.15 moles of that will go on the bottom so that the moles will cancel. And if we do that, gets us 0.165 liters of HNO3. And since the other guy was in milliliters, we can multiply that by 1,000, and that would get us approximately 165 milliliters of nitric acid is needed. Any question on any of those steps there? Yeah. It wouldn't in this case because it didn't really specify the volume, so you could leave it in any unit you want. I just personally converted back to milliliters because this guy was in milliliters, but technically speaking, it didn't specifically ask you for a certain unit, so you could leave it in any unit you want. Yeah. Other questions? So again, you can kind of see these titration problems and solution stoichiometry problems. Again, really the same steps. Step 1, equations. Step 2, convert to moles. Again, just using molarity and volume. Step 3, the stoichiometry part, mole-to-mole relationship. And here, a little wrinkle on the difference here, which is number 4 there, using, again, the molarity on the back end there to get to volume. Any question on any of those steps there? And like normal, as we talked about, you can obviously do all this in one big step if you want without getting the numbers in between. It's all good, you know, in that case. All right, let's try one more here. Just make one up. Why not? Let us do, let's see here. What would be the molarity of sulfuric acid if it took 25.5 milliliters of 0.25 molar sodium hydroxide to reach the equivalence point in a titration. If you started with, let's do 45 milliliters of the sulfuric acid. All right, I will do it as well since I just made it up. We'll hope for the best. Let's see how it works out here. Okay, let's take a look. So once again, we're going to start with the equation. So we're going to take all sulfuric acid and react it with sodium hydroxide. Once again, acid-base reaction here. So we should look for water, which is, again, these two guys coming together. So that is going to give us our water. And again, our salt will be these two guys. We want to make sure we write it correctly. So sodium is +1 and sulfate there is actually -2. So it should be Na2SO4. Again, would be the correct formula there. At that point, we need to balance it. So I believe we need to lay up a 2 there and perhaps a 2 there as well. And then we should be balanced at that point. Any questions on the equation? Yeah. I got it because technically this guy right here is H+ and sulfate. And this guy is sodium and hydroxide. So when we put these guys together, that is basically where the water comes from. But we want to correctly put these together. So since sodium has a +1 charge and it has a -2 charge, you got to put it together that way. Yep. And then obviously you want to balance it at the end, like we talked about with the coefficients after you get the right formulas. So that everything worked out okay. Other questions? Okay, so since we have, let's gotta clear this out. All right, so in this case, we are looking for the actual molarity of this guy. The other thing that we're given is that we have 45 milliliters of it that we're starting with in our beaker. It takes 25 milliliters, 25.5 milliliters of our sodium hydroxide that has a molarity of 0.25 molar. So once again here, we definitely can get to moles for this guy. Obviously, we are looking for the molarity of this guy, which would be moles per liter. So we obviously also already have the liters part of it. So the one thing we're missing really for the molarity of our sulfuric acid is the moles, and that's really where the stoichiometry is going to come into play to help us get there. So the only thing we could get to moles of here is our sodium hydroxide. So that is where we should start. We're going to once again make sure we convert our volume into liters. You can move the decimal place 3 places to the left or divide by 1,000. Both end up in the same spot. Using our molarity by getting rid of the big M and replacing it with moles per liter, we can make sure that all the units properly cancel. And if we do that in this case, we get 0.0255 times 0.25 gets us something like 6.375 times 10 to the -3 moles of sodium hydroxide. Here, we're now going to use stoichiometry to go from sodium hydroxide, which we're not interested in, to sulfuric acid. And we can see from the equation, it's a 2-to-1 relationship. So we want to get rid of the sodium hydroxide. So that needs to go on the bottom. So that would be 2 moles of sodium hydroxide and 1 mole of our sulfuric acid. That is going to get us divided by 2. 3.1875 times 10 to the -3 moles of our sulfuric acid. Any questions on that so far? That obviously now gives us the top part of what we need to calculate the molarity. So we have the moles of it. We have the volume that was given to us. We then need to simply divide those two. We do need to also make sure we convert that volume into liters as well. So once again, move the decimal or divide by 1,000, gets you 0.045 liters. Dividing that by 0.045 gets us a molarity of 0.0708. And again, you can leave it as moles per liter, or you can write the big M for H2SO4, or again, 0.0708 moles per liter. Either way there, since the units do not cancel. Any questions on that? So also really important, sometimes people bypass the whole kind of equation. And if you did, you would have obviously the wrong multiple relationship, right? And you would get the wrong answer. So you do want to make sure you don't bypass writing the equation and balancing it correctly. Question on titration problems, solution stoichiometry, solutions, any of those things? All right, that comes to the conclusion of chapter 15.